There's one issue left in the context of scattering experiments. So far we have considered the scattering process in the effective one-body picture. So the target, that was the center of the potential fixed in space, and the projectile has the effective mass mu. Now in real laboratory experiments, of course it's not the center of the potential which is fixed. In a real laboratory experiment we have a genuine two-body problem, and whereas in the effective one-body problem it's the center of mass which is fixed, in a laboratory experiment it's the target, so it's one of the two particles involved which is initially at rest and initially fixed. And this leads to the fact that the angle that we are going to measure with our detector in the laboratory is different from the scattering angle that we had introduced in our theoretical description. So far we have considered the effective one-body problem with the projectile having reduced mass mu with relative coordinates little r of t, and the center of mass being at rest. What we need in the laboratory is we need a genuine solution of the two-body problem, not in the center of mass frame, but in the laboratory frame, and not with the center of mass at rest, but with the target initially at rest. The target doesn't necessarily have to be at rest after the experiment, because there will be a recoil and therefore also the target will move after the scattering process. But initially we have the target at rest. So what we have to do is we have to translate the scattering angle that we used so far to the angle that we actually measure in the laboratory. Let's recall the situation in the center of mass frame that we considered so far. We have the beam axis, we have here the center of mass, we have the projectile coming in, being scattered, and in the center of mass frame the target is, well, the center of mass is at rest, but the target is not at rest. So the target will also perform a motion, it will move on some trajectory, and let's say this here is the trajectory of the target as seen in the center of mass frame. Let's say at some point t the projectile is here and the target is here. Then the relative coordinate is this vector here, little r of t. And this is the relative coordinate that we used in the description of the effective one-body problem. If we have the origin of our coordinate system in the center of mass, then the projectile has position r1 of t, the target has position r2 of t, and the difference between the two is the relative coordinate r of t. Now when projectile and target are far away from each other still, before the encounter, then asymptotically they move parallel to this horizontal beam axis that I drew. After the scattering, or long after the scattering, again they move uniformly along straight lines, but this other asymptotic straight line is tilted against the original beam axis. And the angle between the two, that is the scattering angle theta that we had introduced and that features in our formulas. That's the view in the center of mass frame. Let's now look at the lab frame and let's see what changes. Let me again denote by the horizontal line the beam axis, but the black dot, which represents the center of our reference frame, of our coordinate system, no longer corresponds to the center of mass, but the origin, this black dot, now corresponds to the target, which is one of the two bodies, one of the two particles involved. And more precisely, it's the initial position of the target. And initially, the target is at rest. Then comes the projectile. It's again scattered off the target. But in the lab frame, the position of the projectile is characterized again by a vector r1, but it's a different vector now because it's the position relative to the initial position of the target, and it's not the position relative to the center of mass. So we have to use a different symbol here. It's r1 prime of t. Yeah? So that's the position vector of the projectile in the lab frame. The target, when the projectile bounces off the target, then due to momentum conservation, there will be a recoil, and the target will start to move. So after the scattering, the target moves away from its initial position, and its position relative to its initial position is r2 prime of t. In the center of mass frame, I showed the relative coordinates, the distance vector between the two particles, the two bodies. That's the red vector r of t. That's r1 minus r2. Now the lab frame differs from the center of mass frame by simply a uniform motion, the uniform motion of the center of mass. If I consider the positions of the two bodies at a certain time t, then for the projectile, say I have the position here, and then for the target, I have the position here. So r1 prime and r2 prime. And the difference between the two, the distance vector between the two, that's again r of t. So it's the same vector as in the center of mass frame, because the uniform motion of the center of mass that enters into the transformation between r and r1 and r1 prime and r2 and r2 prime, that cancels out when you take the difference, and hence the distance vector r of t, this relative coordinate, is r1 minus r2, and it's also r1 primed minus r2 primed. What is the angle that we measure in the experiment, that we measure with our detector? It's the deflection angle of the projectile with respect to the beam axis. So long after the scattering, both projectile and target will move uniformly. Again, they will move along a straight line. The projectile will move asymptotically along, say, this straight line here. And the angle with respect to the beam axis is the angle theta prime, which in general is different from the theta on the left-hand side in the center of mass frame. The question is, how do we get from theta to theta prime. What is the relationship between the two? Let's look at the situation sort of long before the collision and long after the collision is over. So before the collision, at time minus infinity, in the lab frame, the projectile moves with velocity vector v1 primed. And the target is at rest at time minus infinity. The center of mass of the two particles is moving with respect to the lab frame. The center of mass is moving in the same direction as the projectile with a velocity capital V. This is the velocity vector of the center of mass relative to the lab frame. This implies that the difference between these two velocities must equal the velocity of the projectile as seen in the center of mass frame. So this must be the velocity of the projectile in the center of mass frame. This is equal to, we set the position of the projectile in the center of mass frame. This is our vector r1, and the time derivative of that, r1 dot, this is equal to the velocity in the center of mass frame. What's the situation after the collision? Long after the collision, so with time going to plus infinity. Let me indicate here the beam axis. It is still true, it must still be true that the velocity vector of the projectile viewed in the lab frame must be the sum of the velocity vector viewed in the center of mass frame plus the velocity of the center of mass in the lab frame. So it must still be true that v1 primed vector is equal to v1 plus capital V. Only that these vectors are now no longer parallel to the beam axis, but they are tilted with some angle with respect to the beam axis. So let's say in the center of mass frame, the projectile now has a velocity vector v1, and the angle with respect to the beam axis is our scattering angle theta. The center of mass still moves with respect to the lab frame with the same velocity capital V, because the center of mass performs a uniform motion that doesn't change at all during the scattering process. So the center of mass still moves with respect to the lab frame with velocity vector capital V. And it's still true that the sum of these two vectors, of the green and the red vector, must give the velocity vector v1 primed of the projectile in the lab frame. Now the blue vector is tilted against the beam axis by a different angle, and that is the angle that we measure in the lab. That's the theta primed. Now in this geometric picture we can calculate certain lengths. We can say, for example, this length here, well, this is just the velocity of the center of mass, absolute value, and we denote that simply by a capital V without the vector symbol. this length here, this is the length of the projection of the green vector V1 onto the beam axis, and this is the absolute value, the magnitude of V1 times the cosine of the scattering angle theta. And this vertical length here, this is V1 times the sine of the scattering angle theta. Now we can calculate the tangents of theta prime, so the scattering angle observed in the lab frame. For this purpose we have to consider the triangle with the that involves the blue vector, and the tangent is the height, which is V1 times the sine of theta that we had just indicated, divided by the horizontal length, and the total length of that side of the triangle is V1 times the cosine of theta plus the capital V. We can slightly rewrite this as the sine of theta divided by the cosine of theta plus capital V divided by little v1. So this is the first formula that represents the relationship between the two scattering angles measured in the center of mass frame versus the lab frame, theta and theta primed. And this formula involves the ratio of capital V, so that's the velocity of the center of mass, and v1, which is the velocity of the projectile in the center of mass frame. And if we find that ratio, then we have the relationship between theta and theta prime. So that is a task that remains, that we should somehow determine this ratio. Now, in order to find this ratio of velocities, we invoke conservation laws. We use first momentum conservation. We consider momentum conservation in the lab frame. Now, in the lab frame, the center of mass moves with velocity capital V, and the total momentum of the two bodies is, as I said on the left-hand side, total mass times velocity of the center of mass. And that's constant throughout the scattering process. I can look specifically at the situation at time t going to minus infinity, so long before the encounter of the two bodies. In the lab frame, the second body, the target, is at rest at time minus infinity, and only the projectile moves. And the projectile has mass m1 and velocity r1 prime dot. So the contribution to the total momentum comes only from the projectile, so it's m1 times v1 prime, because we're in the lab frame at time minus infinity. It doesn't hurt if I subtract from that the velocity of the target at time minus infinity, because this is equal to 0. So it doesn't hurt if I do that. But v1 prime, that's r1 prime dot, and v2 prime, that's r2 prime dot. So what we have inside the bracket, this is actually d over dt r1 prime minus r2 prime, but this is the distance vector r. So actually what we have here, this is m1 times change of the distance between the two particles, so r dot at time minus infinity. So this allows us, momentum conservation allows us to express the velocity of the center of mass as mass of the projectile divided by the total mass times the change of the distance between the two particles, little r dot, at time minus infinity. So this is momentum conservation as considered in the lab frame. Next, we can exploit energy conservation. And this we can consider for the effective one-body problem. For the effective one-body problem, we have asymptotically free motion far away from the center of the potential. So far away at time plus and minus infinity, the total energy is composed only of kinetic energy. We don't have a contribution from potential energy. And the total energy must be conserved. So the total energy at time minus infinity is given only by kinetic energy. That's the reduced mass over 2 times the velocity at time minus infinity squared. And long after the scattering process, again, we have only kinetic energy. It's again reduced mass over 2 times velocity, now at time plus infinity squared. This implies that r dot at time minus infinity and r dot at time plus infinity must be equal. That's the consequence of energy conservation. And then finally, the position vector of the first body is given by the position of the center of mass, but this is equal to 0 in the center of mass frame, plus the ratio of m2 divided by the total mass times the distance vector little r. We can take the derivative of that equation with respect to time, and then we get r1 dot, which is V1, and the absolute value of that at time infinity. This is equal to m2 over total mass times change of distance r dot again at infinity. These three inputs allow us to write the ratio of the velocity of the center of mass, capital V, over the velocity of the projectile at time plus infinity. That's what we have in this transformation formula for the scattering angles. We use the result from momentum conservation for capital V. We express that as m1 over total mass times r dot, the change in distance at time minus infinity, and we express the velocity v1 at time infinity with the help of the third result on the left-hand side, that is m2 divided by the total mass times r dot at infinity. Now here it doesn't matter whether we have r dot at plus or minus infinity. We learned from energy conservation that these values are equal, so we are allowed to cancel these out. Likewise, the total masses cancel, and all that is left is that this is the ratio m1 over m2. This we can insert into our formula for the scattering angles. Remember, we had the tangents of theta prime, the scattering angle in the lab frame, that was sine of the scattering angle in the center of mass frame over the cosine of the scattering angle in the center of mass frame, plus that ratio of velocities, and we just found that this is equal to m1 over m2. So this here is the transformation formula between the scattering angles in the two different reference frames. As a consistency check, let us consider the case where the projectile is much lighter than the target, or the target is much heavier than the projectile. In that case, we would expect that there's very little recoil, so that the target, after the collision, after the scattering process, the target still is almost at rest, and therefore we would expect that there should be hardly any difference between the scattering angle in the lab frame and in the center of mass frame. And let's check whether this is indeed the case. So here we have the special case m1 much smaller than m2. In that case, the ratio m1 over m2 is almost zero, and therefore the tangents of theta prime is approximately sine theta over cosine theta, which is equal to the tangents of theta, and therefore indeed theta prime is approximately equal to theta, as we had expected.